Hello, my name is Benjamin. I'm the captain of the Reali drone team. This is our unmanned aerial system. We took as a base model the Turret 960 and then we made some upgrades to it. Like you can see on the photo, the landing skid is made by us. It is better than the original one because it holds the drone while landing in a lot more stable position, and the landings that occur are a lot safer than before. We're using as our autopilot on the drone the Pixoc Orange Cube. We're using the RFD 900X telemetry and two GPS here, and using two 12,000 milliampere hours batteries, and using the Raspberry Pi 4 and the Raspberry Pi HQ camera as our imaging system. In the competition, we will be attempting the mapping mission and the object detection mission, and of course the navigation mission. So here we can see the view from our drone when he is doing the mapping mission and searching then later for the objects that we need to detect. We will not attempt the airdrop mission because we didn't practice for it and didn't try it at all. What about the object detection? We are very confident with that, and almost 90% autonomously doing all the things needed and detecting the object. We would prefer to do part of it manually because we would like to check if it detected all of the things right and did all the things as intended. About the autonomous flight, we're very confident. Our error rate in the waypoint navigation is very small, and we do a great obstacle avoidance. So we are pretty confident about that. And about the mapping mission, we are hoping that it would be better than now, but now there are some still problems, partly with the stitching, but we hope we would overcome it and we will succeed in the competition. So we had a few types of developmental testing. We had the one that we made on ground, like the simulations that we made on our computers and that we made on a mission planner. Also, we used our camera and we played with the focus of it on the ground. So when we would fly into the air, we would have the right focal length in the lens for the height that we want the drone to fly at. So, and we tested all the needed systems like the rotating lidar that is searching for other unexpected vehicles and obstacles at flight. So we tested it on the ground to check if it sees anything. And when we used our lidar for height, so we checked if it sees the right height on the ground and what is the error, and then we fixed it. And this is the first type of test that we conducted on the ground. Other tests that we conducted not on the ground but inside our school is made with a smaller hexacopter drone that we can fly inside our school. We have a big football court and we can't fly big drones there, but we can fly a small drone to understand the form factor, to understand how it flies, what programs we need to do, how to work with it, and we used it in our school that we don't need to ride to our range and waste a lot of time. If something doesn't work, we can go to back to our lab and fix it and try to think about new ways and understanding about how we could make some systems that hold all the things needed. And that's what we used about the second type of the tests. We used a smaller drone to understand the working of all the things that we made and constructed. And now we are about to talk about the third type, that is the real testing of the real deal. We went to our special range and we flew with our drone to understand its capabilities and its vulnerabilities. We tested the different missions. We saw how it would react in different times of the day and in different weather conditions, strong winds, and so on. And these type of tests were to see that we are capable of flying the big drone, and the big drone is capable of doing all the missions that it's intended to do, and with which accuracy it does it, and how it does it, and so on. We made about 40 autonomous flights to check if our big drone is working correctly as intended, because safety is very important to us. We have three types of flights: the autonomous one, and of course the one that the safety pilot takes the lead and tests the drone to check if it can fly normally before we do even the autonomous flights. And the third one is to train our safety pilot to take control of the UAV while he is making the mission, so our safety pilot would be ready for the competition. While we conducted our autonomous flights, the safety pilot took control just 3 times while we were in a very low battery levels that became dangerous to our drone. So we told our safety pilot to take control and land the drone immediately. That's it's a sample of one of our autonomous flights that our drone made. It's navigation and then scanning the area of flight. We had good accuracy in our waypoint navigation. The 1 or 2 missed waypoints per flight were pretty rare, and the misses were because of other factors like strong winds and different other factors that we can't control. For the obstacle avoidance, we're using the bendy ruler method. Here you can see that once the UAV will breach the fence, it will make the protocol of RTL and will show us that it breached the fence. To avoid other aircrafts, we are using the rotating SF-45/B LiDAR that he could detect and find other aircrafts. We tested it on the ground because in the Israeli airspace it's very problematic to test it against other drones. When we put stationary obstacles on the navigation route of the drone always avoided them. We tested the LiDAR that is finding other aircrafts and other obstacles on the ground, and we saw that it detected those other obstacles because in Israel it's problematic to check it. We would maybe try to check it before the competition in the US against some high objects or some controlled other objects in the air. For the imagery system, we are using the Raspberry Pi HQ camera. We set the focus on the ground because we know the length that we need to measure because we know the height that the photos will be taken on. And the quality is really good because we played with some of its shutter speed and other options, and we made the best possible photos. We know the location of the photos that were taken because we are making a special trigger that is connected to a waypoint on the scanning mission. The object detection algorithm works by finding the biggest contour on the picture, then detecting the color, and then detecting the letter and the color of the letter. The mapping algorithm is stitching all the photos it got and then cropping the image into a map and then resizing it to the right size. When we tried the mission demonstration, we did our tests, we sent the data to the judges server, and we found the flaws that the battery time is limited, and we adjusted our program to this limited time. Also, there were problems with the landing skid, so we made our own, and this is the score we got in the mission tests.